As has been mentioned, I mean, really today I want to focus on the concept of biological cosmology. What's the biological element that I feel is underserved, perhaps, in some of the debate about an anthropic principle to date? Now, there is a long-ish quote from Carl Sagan, Pale Blue Dot, wonderful book, wonderful TV documentary, and I think it captures the essence of everything that we're talking about when we're thinking about an anthropic principle in the universe. Carl Sagan says, "That's that dot, right there, is us. On it is everyone, whoever was, whoever lived out their lives. The aggregate of thousands of confident religions, ideologies, and economic doctrines, every king and peasant, every teacher of morals, every corrupt politician, every superstar, every supreme leader in the history of our species lived there on a mote of dust suspended in a sunbeam. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, the Earth is the only world known so far to harbour life." Well, there you go. So what I'm talking about for the next 50 minutes is, do we belong in this universe, and how could we possibly know? How can we bring that question, or hope to bring that question, within the boundaries of legitimate scientific inquiry? Carl Sagan really typifies an orthodox 20th century viewpoint on our relationship to the universe in that passage. And what I want to do is to try to disentangle what is science from what is common sense, and show, as Simon Conway Morris will be able to follow up in the next hour, that the common sense can be very misleading. Really, we don't know what our place is in this universe as yet. There is some really important questions to be addressed there. Okay, so essentially then, if Zoe catches up with that slide there, right? Those are some of the most fundamental questions of cosmology, right? That is a spiral galaxy, much like our own, and if we could zip outside of our own galaxy, the Milky Way, and look down on ourselves, we would find ourselves in what Douglas Adams referred to as a sleepy western backwater suburb of our galaxy. And some of the most fundamental questions we can ask ourselves: are we an accident? Was it likely that we find ourselves living there or anywhere else? Could we have been anywhere else? Is there other life out there? Are we likely to be alone? Although you've been meeting those questions under the guise of an anthropic principle and a cosmological perspective, for my work, they are questions that are falling under an emerging discipline, which we know as astrobiology. And I think that Professor Wise yesterday probably gave you a good insight into the fact that astrobiology is this emerging interdisciplinary science which is really seeking to sew together traditional scientific disciplines to answer some of those cosmic questions. I work for NASA Astrobiology, a distributed institute, which has about 15 teams all over the USA, contributing various angles to answering those sorts of questions. And I think really the only part that's worth reading from this slide is the first sentence there, where they describe astrobiology as the study of the origin, evolution, distribution, and future of life in the universe. To my mind, there is nothing unscientific about that inquiry. It's no more unscientific than the cosmology which sought to understand how and why the heavenly spheres move about when we look upwards into the sky. I should warn you, if in case this isn't already apparent to you, that that view, that this is straightforward, legitimate, orthodox science, is one that meets varying levels of resistance within orthodox science right now. My colleagues at UMBC in the biology department really regard this as rather edgy stuff. They're not really sure what we can say scientifically about the origin, evolution, distribution, and future of life in the universe. So what I want to try and put forward today is where I think the state of science is, and what are the questions that can be addressed and probably will be addressed within the next 10 to 25 years. Now, one more visual to get us started, and again I hope that I'm not overlapping too badly with what you've seen already. This time it's an actual telescope shot that was performed looking towards the center of our galaxy. The illustration in the lower half of that slide shows you what we're doing. We've got a telescope pointed, looking through the disk towards the hub at the center of our spiral galaxy. And if Zoe presses one more forwards, we see the result. This is the image from NASA's Spitzer Space Telescope, showing hundreds of thousands of stars crowded into the swirling core of our spiral Milky Way galaxy. We tend to think of space as being vast, empty, cold, and dark. Indeed, Carl Sagan said as much. And, of course, to a first approximation, that's true. But this shot, I think, gives us at least pause for thought to realize that there is an awful lot out there. As you pause to look into the center of our galaxy, it turns out to be a place of surprising light, crowded with stars, and begging the question from us as to what we expect to find as we explore. Okay. There are really two extreme possibilities here. One is what we might call the Star Trek universe. A universe in which all of those stars, or the majority of them, contain planets that are not only suitable for life, but have actually had life evolved upon them. A universe that is teeming with alien life. The other extreme is that Star Trek belongs to a rather low-budget TV studio somewhere in LA, and that the reality of space is indeed that we're very much alone, it's very big, very dark, and our place is rather unique. Understanding where we are on that spectrum, I think, is the point of the scientific inquiry that astrobiology is setting out to address. And really, we can trace a lot of the formalization of this thinking back to Frank Drake and a conference that was held in the middle of the Cold War to ask the question, what would be the probability of finding intelligent, communicative life out there in space? Just as a quick aside, it's perhaps a sad comment that many of you may already be familiar with, but so many of the more interesting and edgy questions in science get asked through military paranoia. It's no coincidence that this question was being asked at the height of the Cold War. I don't want to make too many allusions to bad movies, but let's just point out that if there's one thing that the West, the free West, was frightened of in the 1950s, it's that extraterrestrial civilizations existed and that the commies would get there first. So therefore we saw some actual funding for this question, and the conference that was convened, Drake was the one who suggested, if nothing else, we can develop a simple equation to ask the question, what would be the likely number of communicative intelligent civilizations? The equation he came up with is shown at the bottom there, and essentially it's just a number of factors multiplied together to give us our magic n. What are those terms? Well, in short order, he says it's the rate of star formation in our galaxy, times the proportion of those stars that form planets, times the number of those planets per star that can support life, times the proportion of these planets where life actually evolves, times the proportion of these planets where intelligence emerges, times the proportion of these that achieve interstellar communication, times the lifetime of those civilizations. And the point of his equation at the time that he put it forwards was to say how little we actually know about it. Well, a secondary point is to say almost any numbers you plug into that suggest life is out there in our galaxy. Why? Because the number of stars in our galaxy is so utterly vast. But the secondary point would be how little we knew back then in the 1950s about the appropriate values to place on any of those factors. Now, before we go further, I'm going to point out that we today are not so terribly interested in the last two of those values. The proportion of civilizations that achieve interstellar communication and the lifetime of these civilizations, it is a form, a dimension of astrobiology, but more and more, even astrobiology is shuffling that off to one side and saying that that's a bit of a side issue. That's becoming more and more the remit of SETI, the Search for Extraterrestrial Intelligence. A fascinating group in their own right, although they're now privately funded by philanthropic concerns. They are explicitly interested in messages being sent out to space from us and messages being received from space by us. Fascinating individuals. I've been privileged enough to bump into a few of them over recent years at various conferences, and I'll just draw your attention to one in particular, Doug here, who is the real-life Jodie Foster, for those of you who've seen the movie Contact. Doug is a great guy, and he has the enviable job title of Interplanetary Stellar Message Composition Director. And that's a business card which I take to my door just to remind me how mundane my job is as a professor of biology. But for our purposes today, we can drop off those last two factors, and we can focus on what we have left. And these are the numbers that I want to think about for the remaining 40 or 45 minutes. Now, the truth is that since Drake put forward this equation, we've come a very long way, not only in placing numbers on some of those factors, but on radically changing our opinion about what those numbers should be as our instrumentation has improved. Let's start at the beginning, with the rate of star formation in our galaxy and the proportion of stars that form planets. Perhaps the number that we've been most confident about for the longest, and that even Drake would have been confident of, would have been the number of roughly 100 million stars within our galaxy. That's the number we're dealing with. And that was his point of departure for the discussion, is to say that with a number like that up at the top, as long as none of those other factors sink to an absolute zero, we're likely to be talking about life out there in our galaxy. More recently, we've made a lot of progress in the broader scientific community with the second of those values, the proportion of stars that form planets. If you'd asked cosmologists, astronomers, up until about 10 years ago, what was the proportion of stars that form planets, they would have placed it close to zero. The fact that our planet exists was something of an anomaly and something of a mystery. Recently, that value has gone through quite a U-turn and has reached almost the opposite conclusion based on new experimental data. It's not clear yet, but the speculation is that it could be that most, if not all, stars in our galaxy contain planets. And right now, we're looking at the launch of spacecraft from NASA, which are going to answer the remaining debate with empirical certainty. So far, the only planets that can be detected, and many of you may be aware of this, are the very, very large ones, which actually cause slight wobbles in the amount of radiation received by Earth or by space telescopes as they look at stars. And as giant planets go around those stars, slight variations in the amount of brightness reaching us can give away the existence of those large planets. But as instrumentation is improving, and our ability to detect planets is improving, it turns out there are far more of them than anyone had suspected. And now we have spacecraft that are dedicated to finding out whether it is indeed true that most, if not all, stars out there in our galaxy contain planets, perhaps far more Earth-like planets than had previously been guessed at. We don't know for certain, but I think it would be legitimate in 2009 to say that the second number could indeed be close to 1. So we could be dealing with 100 million carried through to the second of those factors. That leaves us, that leaves us looking at the next two variables, which are really the core of where biology gets involved in this whole way of thinking. The number of planets per star that can support life, and the proportion of these planets where life actually involves. Now, the skepticism of my home department back at Maryland, my biology department, about my interest in astrobiology is, of course, that we only know one example of biology so far, and that's the example of biology that we find here on our home planet. But I think it would be naive of us to suggest that there's nothing useful we can learn by looking carefully at what we already know about life on Earth when it comes to asking about the number of planets per star that can support life. In particular, if there's one thing that has become very clear over the last decade or two within biology, it's that life on Earth got off to a very early start. A timeline shown down the right-hand side of this slide illustrates the 4 billion year-ish history of planet Earth. And although all of the interesting stuff from a classical evolutionary account would occur within the last 600 million years, that's where multicellular life, including plants, animals and fungi, really got going. When we're looking for the origins of life, it would now appear that the oldest signs of life that can be detected according to isotope data date back to pretty much 4 billion years ago. In fact, there's a paper here, and I won't lie to you, it's not without debate, but there's a paper here from Nature back in the mid-1990s that suggests isotopic data from microfossils that we find existing in rocks, some of the earliest rocks that we can find on planet Earth, that would date back to as much as 3.8 billion years ago. So life on Earth is getting off to a very early start, particularly if you rewind your view of what planet Earth looked like to a little bit further than 3.8 billion years ago. If we go back to 4 billion years ago and beyond, Earth is an incredibly inhospitable environment for life. We're still working hard on understanding what boundaries exist for life on Earth, but we can be fairly confident that beyond about 4 billion years ago, Earth was incredibly hostile and unfriendly to the presence of life. It was a planet that was still in the latter stages of formation, and our best understanding of how a planet forms is by the accretion of large blocks of matter that start as grains of dust, and then grains of dust attract other grains of dust through gravity, they become meteoroids, asteroids, bolides. These things are impacting one another and gradually forming planetesimals that in their final stages, the largest one is attracting the smaller ones, and in a series of very violent collisions is producing our planet. And up until about 4 billion years ago, Earth was still being hit with the last of these planetesimals. In fact, an orthodox view of the origin of our moon these days is that one of the final impacts was so large, as sort of illustrated in an artist depiction down there, that almost like a ball of wax hitting another ball of wax within one of those old hippie, what do you call them, wax, lava lamps, thank you, right, that would have knocked out another ball, which became our moon. And so that's the sort of incredibly violent impact event which NASA rather euphemistically calls a sterilizing event, setting a lower boundary on when life on Earth could have got started. And that would have occurred a little over 4 billion years ago. So separating what we now think may be the oldest fossil signs of life and these incredible sterilizing impacts that occur in the latter stages of planet formation is one simple and significant event, which is the cooling of our planet from a ball of molten rock to contain liquid water oceans. Now, the team here in Hawaii, this is their focal point, is to understand the origin of Earth's oceans. But what we can say is that in a relatively narrow window between planet formation and the emergence of life, that one significant event occurred, the formation of watery oceans on planet Earth, and then very rapidly, in short order thereafter, the emergence of life on Earth. And that is a lot of preamble to tell you why I think it is that we can say something significant about the probability of life evolving when we look at our single planet. Now, I know that Simon Conway Morris has a different view on this, and I'll leave it for him to expound that in about an hour's time, but I would at least put that visual in front of you right now and encourage you to probe that with us in panel discussion. It would seem to me as if life was in some sense pregnant on our planet from the very inception of what we think of as Earth. Okay, so we're looking now at 100 billion stars in our galaxy, many, most, perhaps even all of them containing planets, and we're talking about those planets perhaps being very ready to give rise to life, provided they cool down and provided they have liquid water oceans. That, of course, explains why NASA is so fascinated with the presence of water, or the putative presence of water, on solar system bodies, which it is exploring right now. There seems to be that tight correlation between water and life, at least in the one example we know. It may not be necessary, but it would be a fairly good conservative start point for thinking about life elsewhere, to say if there was water on Mars, or if there is liquid water on Europa, is there life, and if not, why not? But that leaves us with the all-important evolutionary question. If we're talking about a very large number of planets, many of which can support life, and many of which life can potentially emerge on, what is the proportion of those planets and those life systems that are likely to evolve intelligence? And that leads me back to the talk that I was giving yesterday, when we asked this question, according to orthodox evolutionary theory, is it likely that the natural processes responsible for evolution would lead to something like us? And I called into question and criticized the image that you see before you there, which terminates, as usual, with a white male. The point that I was really trying to labour yesterday was that Darwin's focus was on natural processes that can be described objectively within the boundaries of legitimate science, and that when you place those limits on our understanding of how life changes over time, it leaves us very unsure about what it means to talk about progress or increase in complexity or an increase in sophistication over a 4 billion year period. Darwin's view tells us that every species on today's world is the successful product of 4 billion years of evolution. It would be an imposition of cultural values, according to Darwin's theory, for us to state that some of these species that we find ourselves sharing the planet with are in some senses lower or less highly evolved than we are. That is not a statement that can be adequately or clearly assessed within evolutionary science. And that, of course, is very different from the pre-Darwinian views of evolution, which gave us or mapped evolution onto the notion of a scala naturae. And it was questioned yesterday as to whether there aren't objective measures in the wings waiting to rescue our sense of humanity as being an extraordinary product of evolution in some objective way. Perhaps we could take information theory and apply it to ourselves in such a way that we show ourselves to be the most complex outcome of evolution. Well, I said that I would find the data for this, so I've shown you in a little table there an examination of the amount of coding DNA found in different genomes of different organisms. Mammals are shown at the very top there, and the scale running left to right shows the size of genomes when we cut out as much of the junk as we're able to. And human beings exist right in the midpoint of mammals, so there are plenty of mammals that contain more DNA than our species. And perhaps more sobering is that as we look down that list of other groups and the amount of DNA that they contain, we find all sorts of organisms, including, perhaps most notably, a lot of single-cell creatures, protozoa such as amoeba, that contain far more DNA than we do. So this is what I mean when I'm saying that by an objective criterion, it is not clear that evolutionary progress was leading to something more complex, namely us. Okay. And so yesterday I was saying that Darwin was very cautious in his use of the word evolution because it came with such baggage by the time that he was writing. The word evolution referred to the unrolling of a plan, the unfolding of a preordained system of creation. And the second question that I wanted to return to really bring home this point again, is to say, well, okay, but isn't it necessarily true that we are products of evolution, and therefore we should regard ourselves as, in some senses, an inevitable outcome of the non-randomness that evolution produces? And the answer is a subtle yes and no. We're an outcome of evolution in the same way as a hand of cards is an outcome of a dealer. If you can actually watch those cards turning up, then once you look at your hand of cards, you can say it was an inevitable outcome. Why? Because as each one you turn up became reality, the possibility became smaller and smaller that you could arrive at anything other than the hand of cards you actually end up with. The question that is of interest when we really want to think cosmologically about evolution is, could we in any sense predict that hand of cards if we could rewind and go back 4 billion years? And that's where Simon is going to be saying a lot more, but I just want to give my 2 cents worth for the rest of today. A key point here is to ask, what do we mean when we talk about survival of the fittest? Now again, I'd say that that was a phrase that was not invented by Darwin. That was a phrase that was invented by Herbert Spencer. And it was a phrase that he invented really because of its cultural value to Victorian imperialism. Survival of the fittest implied that might is right, that civilization and the civilizing influence of the British Empire was a good thing. Why? We fought our way to the top and we're able to colonize, therefore we have something better to offer those that we colonize. Now Darwin was able to embrace that phrase later on and say, yes, in many senses that encapsulates what I'm talking about. But a careful reading of Darwin reveals that the concept of fitness is not an objective and absolute one, at least according to what we can measure by today's standards. Fitness is something that refers to a fit between an organism and the environment. I try and make this point to the students when I'm teaching intro evolution, that we often think of fitness in terms of being able to do push-ups, big muscles, that kind of fitness. I would much rather that we think of this survival of the fittest. It's a bit of a play on words, but we think of it as a survival of those that fit their environments the best. And environments are very complex places. So the concept of what would be a fit mutation that would be favoured by natural selection is entirely dependent upon the context in which a species and organism finds itself. For example, a fly, by its very name, does one thing, it flies. And yet we've found that there are fly groups that have been selected to lose their ability to fly, that essentially become walks instead of flies, because they live on small islands where a breath of wind would blow them out to the ocean, and that would lead to an untimely evolutionary end of that lineage. So there's nothing that necessarily is driving fitness towards any absolutes of complexity or improvement. Rather, there is a constant process of fitting organisms to whatever is required here and now. And there are all sorts of complexifying variables that complicate the process of what is the fittest thing to be here and now. One of the big players in this would be the process that used to be known as continental drift, and today we would know as plate tectonics. which means that even an organism which is inhabiting the same piece of land for a geologically significant period of time is going to experience rapidly different climates. Not only because that piece of land itself is likely to drift around on the face of the globe, but as other pieces of land drift around the face of the globe, they change wind patterns, they change rain patterns, they change the environment. Now, a secondary point that I want to make here is that very often when we think about a fitting of an organism to its environment, we think in terms of non-biological factors. The amount of sunlight, the type of soil, the amount of rain, and so on and so forth. But again, a careful reading of evolution, and one of the big sort of re-examinations of evolution during the early 20th century, was to realize that most of what organisms are evolving to is other organisms. It's not about fitting yourself to a non-biological set of factors. Rather, it's about outrunning the predators and outrunning the prey, making sure you can catch food without becoming food, making sure that you can attract mates, making sure that you can compete with other males to secure mates, making sure that you can dupe other organisms into pollinating you as a bee orchid, making sure you can dupe other organisms into not seeing you because you resemble a leaf, catching other organisms for food, fending them off with thorns, whatever it is we choose to think about. Evolution is, I guess the Hindu would think about the dance of Shiva, this incredibly intricate dance in which every move made by every player has a ripple effect on all the other players. As thorns grow longer and a plant becomes less palatable, that forces an organism to start looking at another plant, or itself to evolve further protection against those thorns, or further behavioural manipulations to be able to get around the plant. And that in turn will affect what the animal is like that is now dealt with by parasites and predators of its own. This whole rippling, complex jigsaw is one in which the long-term outcomes of evolution are not any sort of common sense or intuitive objective functions. And I'll just return to continental drift for a second. I want to point out that although when we look at a geological timescale, we can very often smooth some of these complexifying factors into rather gradual looking functions, they need not be by any stretch of the imagination. I think it was extremely sobering to all of us who lived through it to see the tsunami that was caused by a minor catch in two plates that should have been drifting apart in the not the Indian Ocean, in the Asian region there next to Indonesia in 2003. And the pictures, say, of Banda Aceh remind us that the consequences of this seemingly graceful drifting of plate tectonics can be devastating within a short-term ecological time frame. And that's the sort of contributing factor that we have to think about when we're asking about long-term evolutionary trajectories. Perhaps more common and more familiar to all of us these days would be the concept that during geological periods of evolution, things are not always business as usual. We call ourselves the age of mammals, the Cenozoic, and yesterday I questioned that by thinking about species diversity that we find in the world today. Today, I just want to point out that the reason that we do call it the age of mammals is that the last 65 million years has seen enormous diversification of mammal lineages. But that enormous diversification, and I think it's fairly common knowledge these days, itself owes its origins to a fairly catastrophic impact, this time from outer space. For a long time this was hotly debated, and even today there are worthwhile debates taking place as to how necessary this cometary impact was for the evolutionary transition that we saw. But I think it's beyond doubt to say in 2009 that a huge and unimaginably severe impact by our human lifetime standards was responsible for a very dramatic and geologically rapid turnover in the species that we find on planet Earth at precisely 65 million years ago. And if we look back before that 65 million years to the Mesozoic, the age of reptiles, we're talking about the age of the dinosaurs. And in common parlance, we use dinosaur to refer to something that is old or lumbering or outdated. And it's not at all clear that that is actually an accurate depiction of the complex and sophisticated fauna that we found populating Earth before the mammals ever really got going. Perhaps the poster child for this way of thinking or re-evaluating the reptilian age would be the ichthyosaur, the dinosaurian equivalent of a dolphin. There's two artist depictions of it, And really, even as an undergraduate, that's something that we're introduced to say, isn't it amazing how convergent these lines of evolution could be? Reptiles seem to be doing very well for a period of almost 200 million years, and it may well be that that asteroid impact wiped out a fully functioning ecosystem, not because it was lumbering and ancient and primitive, but because it had the bad luck to be there when the asteroid collided. Okay. And Zoe, you're doing a very good job of catching up, thank you. But this process of mass extinction is, of course, responsible for the various divisions that mark up geological time when we look at long-term evolutionary trajectory. Every time we look at a distinction between, say, the Jurassic and the Cretaceous, we're looking at a major turnover of organisms. And when we're looking at the turnover between eras, the Paleozoic, the Mesozoic, and the Cenozoic, we are looking at the mass extinctions which seem to have abruptly and without much fairness wiped out perhaps the majority of organisms that were thriving on Earth up to that point. The biggest of the mass extinctions, at least in terms of multicellular life, would still seem to be that which occurred at the end of the Paleozoic and ushered in the age of reptiles itself. And this time, at least according to some estimates, it would have been about 95% of known life that went extinct. It's not clear what the cause was this time. People have been suggesting asteroid impacts for a number of years. They've also suggested supervolcano activity, quite beyond anything that we can imagine when we think about the volcanoes that we are aware of within our own lifetime. It's quite possible that actually the two were connected, and that a suitably large asteroid impact would actually provoke the kind of volcanic activity which would further degrade the environment in a geologically sudden manner, and in a way which natural selection, at least in terms of long-term smooth trajectories, would be entirely ill-equipped to handle. In fact, if you can sort of wrap up all of that into a thought, it's a thought that actually predates a lot of what we now know about mass extinction. And the thought we can trace back to Georges Cuvier, the pioneer of fossil reassembly from Lake Enlightenment, France. And he was one who pointed out that really the astonishing thing about life is that to a first approximation, it isn't. The vast majority of organisms that have ever lived on planet Earth apparently have gone extinct. And we're talking here about 99.9% of those that we can detect in terms of species, as species which are no longer with us. So extinction, and perhaps extinction due to capricious cause, are overriding and dominant features of long-term evolutionary trajectories. Okay. I'm going to skip over... No, actually, sorry, Zoe, I'm making you catch up with me. We'll go back to the Beatles again. I mentioned yesterday this concept of looking at life's diversity and asking what our place is relative to the organisms we find around us today, and pointing out that insects far outstrip mammals, far outstrip things with backbones in terms of species diversity. If we actually rewind and go back to the origin of multicellular life, we would find a surprising diversity of invertebrates even there. There's an artist's depiction of the Burgess Shale fauna, which is, of course, what Simon Conway Morris first came to public attention by really doing the excellent work to reevaluate what it was that we were seeing when we looked at these animals from around 550, 560 million years ago. I feel bad talking with Simon in the room because this isn't my area of expertise. But let us simply say that those organisms were highly sophisticated, highly complex, and at least in some ways, they were non-representative of things that we find around us today. Again, a poster child for this way of thinking might be this guy, Opabinia, shown there in fossil form and in an artist's reconstruction, which is quite unlike anything that I think, Simon, you can correct me if I'm wrong, but that this is still regarded as something fundamentally different from any organism that we find ourselves sharing the planet with some 550 million years later. Now, all of this way of thinking, that the diversity has been there throughout, that capricious events have dominated long-term evolutionary trajectories and frequently interrupted any sort of evolutionary trends that we might expect to see. All of that comes together into a 20th century orthodoxy that although evolution in any given short interval may be somewhat predictable in its outcome, we may be able to look at the environment and predict what sort of an organism would fit it, or we may be able to predict how organisms may change in the short term to improve their fit to their environment. But if we look at this much longer term, we come up with something that is far more unpredictable and far more difficult to assess in terms of trends or likely outcomes. And towards the end of the 20th century, that was a view that was really championed by Stephen Jay Gould, an American popularist of paleontology and evolution, who created the soundbite that if we could somehow rewind and rerun the tape of evolution, would we find a world that looked anything like the one that we see when we look around us today? And this was the thesis which he sought to address in his book, Wonderful Life. He suggested that there was a careless orthodoxy, more in tune with a scala naturae, that suggests that life has indeed been steadily growing more complex and more sophisticated over time. And he suggests that when we actually take into account plate tectonics, meteorite impacts, the overwhelming presence of extinction, and the fact that fundamental diversity has been with us for a very long period, we may well see that these long-term evolutionary trajectory is more one of near-random winnowing of evolutionary lineages, and that what we see ourselves left with today really is best regarded as a hand of poker, and every time the dealer dealt it, we would end up with an unimaginably different hand. That was Stephen Gould's take on what the Burgess Shale was telling us, and what the message was after 150 years of thinking of Darwin's ideas. Now, I'm actually going to skip forwards too, Zoe, there, and say I don't want to cut into what Simon is going to talk to you about, but simply to say that he has done a great favour to the science of evolution by re-examining Gould's claim in a book called Life's Solution. And his point was not so much, I think, and again I'll let you speak for yourself, Simon, a bit later on. I would say it's not so much to say that Gould was categorically wrong, but to say that Gould's synopsis and Gould's thesis is riddled with common sense and intuition, which is at least open to serious scientific debate. The touchstone of Simon's argument here is evolutionary convergence. The fact that just because it's not intuitive that long-term evolutionary trends exist, that doesn't preclude them from being very real. And one of the ways in which we can get the hint that non-intuitive outcomes may be far more predictable than we would speculate comes when we see structures, complex structures, or complex morphologies that have appeared more than once independently in the course of long-term evolution. Again, I will limit myself to just one of the most famous examples of evolutionary convergence, and one that is regularly treated in even the most cursory introductory courses on evolution, although it's usually regarded as something of a curiosity. And that would be the overwhelming similarity of the complex eye that we would find in vertebrates, such as ourselves, and that we would find in mollusks, such as squid and octopus, the cephalopods, the most sophisticated, if we choose to apply that term, of the invertebrates. The number of convergent features of these eyes is indeed quite remarkable. And one way of reading this is to suggest that there really is a good way of making a large, complex, light-receiving organ, and that no matter how many times evolution has set the challenge of using light as a primary medium for gathering information about the local environment, it will arrive at something more or less like the same solution. Now, I say that even in my upbringing that was treated as something of an evolutionary curiosity. Simon's point is that we may have done great disservice to the sheer degree of convergence which we find all around us. And I'll leave him to describe that in far more interesting detail in his talk, and move right on now to point out that there is a limitation in how far we can go with asking about evolutionary predictability if we limit ourselves to the emergence of convergent features. Essentially, when we find convergence, we're performing a type of evolutionary analysis that is known as the comparative method. This is a method that builds an evolutionary tree in order to ask whether a particular morphology appears to have arisen more than once independently. And the key here is independently. When we look at the gross morphology of a dolphin and a fish, and perhaps even a penguin if we see it swimming, we see similarities. And the question is, can we be sure that those similarities are non-random features produced by the predictable process of natural selection? And the way in which we gather evidence to answer that in the affirmative is to say yes, providing each time we find that morphology, it has arisen from an independent start point. So in the case of this particular morphology for swimming, The answer would be a clear yes. Dolphins are far more closely related to mammals with 4 legs that walk about on land, and penguins are far more closely related to birds with wings and legs that would flap and walk. And so when we find their morphology has converged upon that of a fish, we can see this independent arising of a morphology, and we can draw the inference that that is a good morphology if you choose to swim through water. It's a robust and satisfying method for saying that some features of evolution may be predictable outcomes, but it comes with the limitation that it only works if we can establish independence. And let us take a counterexample here to show you what I mean. All insects tend to have 6 legs. And we could ask the question, is that because 6 legs is a peculiarly adaptive fit, good adaptive fit between organism and environment? If we were careless, we'd say yes, the very fact that we find so many 6-legged creatures shows us that that's a very good and non-random expectation of evolution. But the problem is that all of those 6-legged creatures share a single common ancestor that, as far as we can tell, also had 6 legs. So the fact that those 6-leggedness is retained in all of these modern lineages may be because 6-leggedness is a very adaptive way to be. Or it may be because there's not been sufficient reason to change 6-leggedness. The point here is that evolution tends to build on increasing layers on an infrastructure where the lowest layers become locked in as further adaptations arise that only make sense in terms of the way that you're already doing business. So it may be that 6-leggedness is a feature which has driven all of insect evolution, and that the forms that we find today are forms that have been constrained by the idea that these things are using 6 legs to get around them. And we would be foolish to say that the very presence of 6 legs as a feature that is very common in today's world is one that is itself adaptive and therefore predictable. Now that becomes very relevant when we're asking about our place in the universe, because so much of the fundamentals of life on Earth are things that are universal, that are shared across the whole of life. When we look at a modern genetic view of life's classification, it may well be that plants, animals and fungi are now reduced to a small twig on this 3-pronged tree of life. But it turns out that an awful lot of fundamental biochemistry and molecular biology has been in place ever since those things first started to diverge from one another. And that's something that was probably happening 3 plus nearer to 4 billion years ago. So a really important question from my perspective for astrobiology to ask is there any particular reason why life on Earth early on took some of the fundamental forks in the road as evolution progressed? Can we say anything intelligent about whether fundamental biochemistry is the way it is for a Gouldian reason of capricious whim, or for a more Conway-Morris reason of convergence upon an adaptive, sensible solution that evolution was likely to find with some degree of inevitability? Now forgive me, but for the last 10 minutes of this talk, in order to show you the sorts of things I'm thinking about, I'm going to have to introduce you to a little bit of molecular biology. For some of you this will be very familiar. For the rest of you, the point I really want to make is it's ever so simple. In terms of modern biology, everything, from bacteria to us, is essentially doing the same thing at the biochemical level. It's taking genetic information stored in DNA, and it is converting that information into living, breathing organisms via the medium of proteins. Proteins are the molecules that are the business end of life. They're responsible for digestion of food in your stomach. They are your hair, your skin. They are just about everything that you can think of in metabolism either is a protein or is something that is made by a protein. And so the essential biochemical foundation for life as we know it is to take genetic instructions and to process them into these rather spectacular molecules we know as proteins. In fact, we call that process the central dogma of life because it is so foundational to everything we know about living systems today. Now, just to look briefly at this system, the point that I want to make for you is that the building blocks of life on Earth are not only remarkably uniform, but they are remarkably simple. I think these days it's probably fairly common knowledge that DNA is a linear polymer in which the individual units are built of just 4 different chemical letters, A, T, C, and G. And in fact, the double helix that's so famous is entirely redundant in the sense that it contains two strands that contain exactly the same amount of information in a mirror image form. All we really need to focus on to think about genetic information is one half of that double helix, in which we find a chain of these letters spelt out, snaking its way down the double helix. And it is nothing more and nothing less than the order of those letters that specifies all of the information required to make an E. coli bacterium, an oak tree, or a human being. Okay, Zoe, I'm going to ask you just to zip forward to that second one then, that says that the area that I'm becoming increasingly interested in my own research is the other half of this, the proteins. And they, once again, are actually a linear polymer. So the information that is stored in DNA is translated into a different type of chemical language. But once again, the chemical language is one that is built like a chain, in which each link is one of a fixed number of chemical letters. This time, there are precisely 20 chemical letters that are used. These are the amino acids of biology. And by choosing which amino acid to add to which other one, building up the backbone, which is illustrated in a cartoon form here as a green underlying backbone, and by taking variable side chains that are attached to this backbone, you build up a long chain-like molecule that is a protein, and different orderings of amino acids give you different molecules that spontaneously form up and contain properties as radically different as being the structural basis for your hair or the enzyme in your stomach that can break down sugar and digest it to give you energy. So we have an alphabet of 20 amino acids that is being drawn into proteins. My first real interest in the question of cosmology and biology was associated with the interface between these two chemical languages. It should be clear, if you've managed to keep up with me over the last 5 minutes, that we have something of a question remaining. We have just 4 chemical letters that are used to spell out all of genetic information. And yet that genetic information is being processed into protein molecules which are built as one of 20 letters at each place rather than 4. So the process that molecular biology talks about is translation, and they mean that quite literally. It is the translation of information in one medium into another medium, where the size of the alphabet is different. The principle at work is very, very simple indeed, and it's essentially the same principle that is at work in Morse code, where we translate a limited alphabet of dots and dashes into a much more complex alphabet of English characters. And that's what biology is doing. It contains a suite of complex adapter molecules whose sole function is to read words of 3 genetic letters all at once, these things known as codons, and translate them into a single unambiguous amino acid meaning. The adapter molecule is what I'm showing here in a grey cartoon-like form. On one end of it, it's carrying an amino acid, and it's ready to swing into action by reading off of the codon, very specifically, that particular word of genetic information, and wherever it finds that word of genetic information, it's going to add its specific amino acid to the growing protein chain. That's the process by which biology is continually processing its genetic information into life. And there's a full set of rules that describe how genetic words are read into amino acids. In this case, we've looked at a single codon known as CA, or written out as CAU, which translates into the single amino acid histidine. If we look at every possible combination of genetic letters, we come up with the genetic code, the set of rules describing which amino acid corresponds to each particular possible word of genetic information. 20 amino acids, 4 genetic letters. Those genetic letters are read in triplets. That gives us 64 possible genetic words, and simply the mapping of amino acids onto genetic words is what we call the genetic code. My work in my PhD, when I was at St Edmunds College, was simply asking the question, are there features of that genetic code which we can say are in some sense non-random or predictable outcomes of evolution? There'd been surprisingly little debate on this in the 2 decades that led up to the work that I did under my supervisor. But the simple observation is that if you look at the chemical properties of amino acids and how they're distributed to genetic code words, a simple visual inspection tells you that it appears to be very non-random indeed. It turns out that amino acids that share similar chemical properties are assigned to similar genetic code words. And we got onto the idea that that might be a product of natural selection. In order to produce a code, wherein, when mutations occur and disrupt the genetic message, the result is not disastrous to the organism that houses that gene. So to cut a very long story short, we were doing computer simulations for 3 years that were asking, if we try and create a random sample of theoretical alternative genetic codes, how many of them would have a property like this? And in what sense is nature's choice of a genetic code special? And the answer that we would come up with was that the code that has been settled on very, very early during life's evolution shows some exceedingly non-random properties. I don't think the details matter here, you're welcome to ask me, but the point that we were trying to get at here is that something as fundamental as the very rules by which genes are read into proteins looked as if it contained a lot of properties that we might expect to evolve whenever and wherever this system appeared in biology. Now that is taking us back towards the origin of life, but that was 15 years ago for me. And really my interest since then has been trying to go back to more and more fundamental units, asking whether life on Earth contains this sort of signature of natural selection that would make it in some sense a predictable outcome. In particular, I want to go back to the last 3 minutes of this talk, 5 minutes of this talk, to the well-worn phrase of a prebiotic soup and the origin of life. The concept of a prebiotic soup we can trace back to early evolutionary thinkers, one in Russia, Alexander Oparin, and one in Britain, J.B.S. Haldane, him of the quip about God's love of beetles, who both at about the same time were wondering how life on Earth ever got started. Their speculation was that the very early Earth was one large chemical laboratory in which primitive oceans contained enough reagents such that the energy that was reaching us from sunlight would have been performing simple chemical reactions and forming some of these building blocks for life. And that was what they were referring to as a prebiotic soup. So they proposed that the primordial sea served as a vast chemical laboratory powered by solar energy, acting on an oxygen-free atmosphere of carbon dioxide and ammonia, and that this became a rich organic broth containing all of the building blocks that went on to form the foundation for life. Although they were talking about this in the 1920s, it wasn't until the 1950s when Stanley Miller, working under his PhD supervisor Harold Urey, put this to empirical test and attempted to simulate the prebiotic soup idea. And by putting these simple, non-biological reagents into experimental apparatus where they were able to feed in an energy source, they were able to ask the question, do we in fact end up with the rich organic broth that had been speculated about? And the answer, which is found throughout biology textbooks this day, because it was so clear, was an overwhelming yes. That some of the most important and central building blocks of all biological life are things that can be produced in relative abundance and ease by this simple system. In particular, Stanley Miller's work was able to show that around half of the 20 amino acids that make up you and I and everything else alive today can be produced by such a simple non-biological system. Now that work was so startling in its clarity of message that it spawned an enormous literature of people who sought slightly different assumptions, slightly different conditions, in order to find out how robust Stanley Miller's work actually was. The answer, at least my reading of it, would be to say that his answer is remarkably robust indeed. Indeed, whether we look at almost any conditions for a plausible prebiotic simulation situation, you end up producing around half of the amino acids that life is still using 4 billion years later. There's been some debate recently about one of the central assumptions, which has caused us to look further and ask whether it is actually necessary that we focus on the primordial oceans as being the source of this rich organic broth. And in particular, we can link here through to observations from physics, which talk about where the complex chemicals are coming from in our universe, and the fact that we are all quite literally stardust. There is no way that we know of making elements as heavy as carbon or oxygen or nitrogen, unless it is through the baking process that takes place at phenomenal pressures within a star, and that then explodes in a supernovae to seed galaxies with dust that contain these elements. But what's far more interesting from a cosmological, biological perspective is that those elements go on to perform their own chemistry throughout the universe. The same processes that are producing carbon, oxygen, nitrogen in supernovae are going on when those elements are distributed throughout the galaxy to produce the building blocks that Stanley Miller was proposing for primordial ocean. But these things are being produced in ice grains and dust grains throughout the galaxy in unimaginably vast quantities. And it would seem these days as if the most likely source for those building blocks arriving on the primitive planet Earth was actually delivery from space. Vast quantities of dust are acquired by planet Earth every day. Here was a recent review paper, 2006, which says that a decent estimate of how much of this cosmic dust is arriving on planet Earth every day is probably the order of 100,000 to 1 million kilograms of extraterrestrial debris. And that extraterrestrial debris is containing the amino acids that Stanley Miller was locating in his experiments. In fact, NASA has gone on to do a lot of work analyzing the meteorites that are floating around there in space. This is a particular famous one, the Murchison meteorite. And when they fall to Earth, careful chemical analysis is able to confirm for us that this sort of chemistry is indeed taking place throughout our galaxy. The organic constituents of a typical carbonaceous chondrite meteorite contain all of these fundamental building blocks of life. They contain not only the ammonia and the alcohols, but also the amino acids and even the bases that we find as part of nucleotides within DNA. Now, my point of interest in this last bit of work is that we typically focus in today's textbooks on saying, isn't it remarkable that around half of the building blocks, half of the amino acids that life uses today are indeed delivered from space daily to planet Earth, and therefore are being presumably delivered daily to all that unimaginable quantity of planets that exist throughout our galaxy. But the bit that we seriously overlook in our current discussion is that a far, far greater number of amino acids is being created throughout space and is being delivered on these same dust grains. It may be that we find 8 to 10 of life's amino acids right there in carbonaceous chondrite meteorites or landing on planet Earth every day. But if we look carefully, we find that there are another 60 or 70 amino acids that are being produced in very significant quantities throughout the universe and that are likewise arising. So presumably, very, very early during life's evolution on Earth, evolution made the choice of a subset of these amino acids with which to start building everything that we've seen emerge ever since. And my point of interest in the last 2 years of research has been the absolute dearth of any scientific inquiry to ask the question, are life's choices somehow meaningful, non-random? I think the real problem there is we don't know how to ask that question yet. And my take on it is that we can use computers to simulate different kinds of proteins that have never existed in nature, to ask whether the choice of amino acids that life has made seems to be a sensible choice. The significance of that to me, from a cosmological perspective, is to say that we may be far closer to a Star Trek universe than anyone has ever guessed. It may well be that the raw constituents of life are present in large quantities throughout the universe, are arising on a far larger number of planets than we'd ever guessed existed, and that within that soup, life is picking out very deliberately a small subset because they make the most sense to build with. At the moment, it is a wide open question, but it remains entirely possible that life's choice of amino acids is very non-random, and that given that choice, the sorts of proteins you can make are themselves very non-random. And that then would create a segue into the sort of world that Simon Conway Morris wants to talk to you about, in which we would find convergent evolution from the most foundational layer on planet Earth. That would be the utter opposite of the Gouldian or 20th century view of capricious, whimsical, unpredictable evolution. I don't think we know the answer yet, but I do think that these questions are becoming scientifically tractable, and I do think that within the next 10 to 15 years, we're set to see the emergence of a scientific debate which is going to put far more rigorous, objective evidence into our vision of whether we are unpredictable and meaningless outcomes of a vast and uncaring universe, or whether actually we seem to be in a genuinely anthropic or at least life-friendly universe, and life-friendly in terms of stuff that we readily recognize were we to bump into it. So thank you very much. That's where I'll finish today.
Thank you very much indeed, Stephen, for that great and fascinating overview, and I'm sure it stimulated plenty of questions. I'm just going to start with a small comment, actually. I was reading the Structure of Evolution, Stephen Jay Gould's last great book, the huge one. You know, I have to confess I haven't read it all, but I was trawling through it because I was doing a talk last week on this whole notion of progress in evolution and so forth. So, and on page 468, I don't know why I remember the page number, but I do, he actually sort of slightly backtracks. It seems that he slightly modifies his position there. It's quite interesting, I found. And he wasn't quite so stringent in that huge tome. He had more ifs, ands and buts about his position than some of the early Gould. So the very late Gould seems to be slightly modified. It's
interesting to me that that's entirely consistent with the fact that he modified his spiritual position quite a lot later on as well, from being a fairly straightforward atheist to being far more open to a lot of possible interpretations. I don't know if there's a significant link there, but thank you for that, and I'll actually check that out. I own the book, and likewise, I've got to say that I've read bits of it.
Yes, right, okay. Good, so we'll go for questions now. Who would like to ask the first question? Yes, let's start here.
Would it be right to say that because of epigenetic factors, these are ones outside the actual DNA itself, you can't really compare complexity to the amount of DNA? Is it not possible, for example, for certain genes to operate to produce different proteins with different promoters and in different circumstances? So direct comparison of complexity with the amount of DNA is not really on.
A very fair point. Thank you for that. I think that really brings up to me this point that I wasn't doing a very good job of describing yesterday. My caution is in any attempt to apply a measure of complexity to the evolutionary process. I think my point would be that you could name different indexes of complexity, and unless you choose very subjectively which one you consider to be important, you're not going to find us at the top of it. And by subjectively, I mean if we take culture or spirituality or consciousness to be our measure of complexity, then of course we find ourselves at the top. But it's not clear to me from an evolutionary perspective why we should consider that to be an underlying purpose to what evolution is doing. So yes, absolutely, very different ways of measuring complexity. Epigenetics would give us very different view on what it means to be complex. I've just put up there the amount of DNA to show there's one that at least is a simple objective index, and we wouldn't find ourselves looking so very special.
Okay, that's generating, I think, on the same subject? Yeah. Same thing, yes?
I'm glad you backtracked a little bit on that, because on that slide that you found and you brought since yesterday's discussion, you seemed to imply that if you use DNA as a measure, then clearly we are not very sophisticated, the most complex organisms as we were hinting yesterday. I think we have to be careful. I agree with you that it is very difficult to find a measure of a clearly defined measure of complexity, but it's also certainly not as simple as let's look at the amount of DNA. It's just like saying let's compare two literatures or two books, and then you say, but this one was written in a language that has only 10 letters, and this one was written in a language that has 30 letters. Therefore, this one is more complex. But it's not that. It's really the amount of information that is conveyed. In other words, the complexity of the ideas and the vocabulary. And look how many complex words and sentences I can make, even with my 10 letters, perhaps, than somebody else was able to make with a language that has 30 letters. As I said yesterday, I tell my children, try to see how much information you would need to describe something in order to appreciate how complex or complicated or artistic or skilled this piece or this product is. My main comment that I wanted to bring is with the issue of catastrophic accidents. You know, for example, that 65 million year bombardment or asteroid or whatever it was that killed the dinosaurs, etc. And people, of course, always point to events like this and say, you see, random. And if that hadn't happened, we wouldn't be here. And so clearly, there is no path to humans or to anything more complex than at least dinosaurs. But what we know from astronomy is that these things, even though they cannot be pinpointed in time or predicted in time, they are well studied. We know their rates. This was bound to happen 65 million years ago, or 15 million years ago, or 265 million years ago. Something was going to come in and redrive evolution one way or the other. Where I agree with you is that, of course, there are many apparently random events. But if you take a longer view as to the distribution of amino acids or the distribution of circumstances, natural conditions, etc., I think there is a case that there was the possibility, or maybe the inbuilt potentiality, to use John Polkinghorne's phrase, for that kind of evolution, in the sense that you didn't like yesterday, meaning progress toward more complex. I don't mean it is deterministic, I don't mean it is linear, but I mean that sooner or later, this complex, random here and random there, was going to produce more complexity.
Sure. Thank you again for your comment. And I think, again, let me just try one more time to try to, let me try and link your comment with your observation about complexity. I think that my reading of Simon Conway Morris and Gould connects very simply to what you're saying about complexity in the following way. Gould essentially made the case, isn't it intuitive when we consider such random and catastrophic events such as plate tectonics and meteorite impacts of significant magnitude, isn't it intuitive that you wouldn't get long-term predictability within this system? And Conway Morris is essentially saying, let's bring some empirical data to bear on this and say that our intuition has never been and will never be a good guide to science. Now, my comparison of that to the measure of complexity is exactly the same point. Our intuition about the amount of information necessary to describe something is very different from an objective measure of the amount of information necessary to describe something. I put it to you that if you asked a child and an entomologist to each describe the amount of information necessary to adequately describe, say, a ladybird, they would arrive at very different amounts of information. And that would be very different indeed from somebody who studied genetics, and probably very different indeed from a poet. And so it's that objectivity of complexity is what at the moment places discussion, for me, discussion of the emergence of complexity or the drive towards complexity outside of the sphere of scientific inquiry. I've yet to see something that is so clear and so objective that we can all agree on, that we can say, now we can do the empirical test, the equivalent of what Simon Conway Morris has been doing for Gould's claim, now we can do that for the claim of complexity. If that measure ever arises, I will be delighted to see that become a scientific debate. The one thing I wanted to try to do yesterday and today is to say that what's prohibiting good scientific debate on that topic right now is our lack of objective measurement. And really, I put up the amount of DNA as a straw man to say there's something objective, there's something we can measure. And yeah, maybe it's the length of a book, and just because a book's longer doesn't make it more complex and more interesting than a shorter book. But that is the sort of problem that we've got here. What is our objective measure? And saying that it's intuitive, I think, brings in the host of problems that we were saying are there all the way from Aristotelian views of a scala naturae through to Gouldian views of unpredictable evolution. Intuition must always be an enemy or at least a combatant of our scientific inquiry.
Stephen, I'm going to pop in a question here. Do you think when we find life on other planets, carbon-based life on other planets, do you think it'll be using the same or very similar genetic code to the one we have here on planet Earth?
Well, yeah, good question, because I think we just don't know. Now, I think Simon would say it probably would be. I think that what we've shown is that there's good reason to believe it could be, and yet there's good reason to say we don't know what the parameters are on the equation yet. If, for example, we found evidence, just thought experiment, if we would find evidence that life made a sensible but not overwhelmingly deterministic choice of amino acids, and that maybe life elsewhere we could draw probabilistically from a pool of 15 and say life is likely to be using 10-ish out of these 15, the simple expedient of adding or taking away or replacing one could have a profound effect on the sort of genetic code you might expect at the other end. Now, right now, we just don't know what are the boundaries on these questions. I think my excitement, personally, is that as a theoretician and a semi-computer scientist, the possibilities for computers to sketch increasingly sophisticated simulations of counterfactual reality is enabling us for the first time to ask that sort of question and bring this sort of objective inquiry to it. I don't know. That's the short answer. And I think I'm delighted whenever I bump into someone who says, I don't know, rather than it's pretty intuitive to me the answer is no, or it's pretty intuitive to me that the answer is yes.
Thank you. Okay, Alan.
When Carl Sagan made use of the Drake equation, he made estimates for each of the 7 unknowns there. And one of them was that when life originates on the planet, the chances are very high that it will progress to intelligence. And the line apparently was that intelligence, consciousness, if you like, to use the term you used a moment ago, that this gives, in some sense, an advantage from the point of view of natural selection, so that, so to speak, there is a progression in terms of, particularly in the last stages, leading through the hominid line, for example, that somehow there is a sufficient selective advantage to make it likely that natural selection would pick, so to speak, favorably on intelligence. So would you say, I mean, you do mention that the humans are in some sense at the top in terms of that very restricted notion of mind and intelligence, consciousness. Are there selective advantages that might in fact guide that sort of direction in a very broad sense?
I think the safest answer, thank you for an excellent question. I think the safest answer I can give is to say that there are widely different opinions on this. And you're about to hear one that's very different from mine in the next talk. My take would be, it's not hard to retrofit an explanation of why intelligence is a good idea. But once again, the empirical data is not overwhelming that natural selection finds intelligence to be something that is so obviously useful, it just keeps popping out of the equation. Generally speaking, outside of humanity, we have what? The great apes, highly intelligent, mammals, the intelligent, and then there would be the cephalopods, the squids and octopi. Now, what strikes me is that the rapid acceleration of intelligence to levels such as we find in ourselves really does seem to be a one-off, doesn't it? I mean, we have perhaps 30 million species on the planet, and apparently once that runaway process has been of enough selective value that it was arrived at. Could it happen again? Entirely possible. Do we know yet whether we're closer to certainty or closer to absolute unlikeliness? I don't think we do. But I'll let Simon Conway Morris give you a very different and perhaps a more considered take on that same question in the next hour.
Okay, I think Simon will probably want to add the crows as well to his list, won't he?
Yeah, there you go. Sorry, that's a good call.
So let's not forget the crows. Right, another question, yes.
Hi, Stephen. This is just a minor, just a very small point clarification on the Drake equation. First of all, I don't understand how I don't understand why the lifetime term disappeared. It seems to me that the lifetime of relevant civilization would be very important. But also, in a multiplication equation, of course, by removing it, you're effectively setting it to 1. So why would one set it to 1? In fact, that's the other thing is, to me, and I'm sure that most people in the room know this, and I don't, but I don't understand the units of that equation. I mean, you have things like, on the left-hand side is the number of intelligent civilizations. On the right-hand side, you have a rate of star formation, you have a lifetime, you have all sorts of numbers. So could you just say a little bit about that?
Yeah, absolutely. Thank you for an excellent question again. The Drake equation, it's almost tradition that I have to use that as my framework for describing these variables, right? I think its usefulness is in thinking about what are the factors involved. And I think taking it as a literal equation is probably less helpful than one might expect. There have actually been at least 2 derivations of it, one slightly later than the first. The first one was considering the rate of star formation, and the second one simply stated the number of stars present at this given moment in the galaxy. because it just seems simpler to actually do the sort of rational, formal equation calculation that you're talking about if we focus on an integer, the number of planets. We stop mixing up our terms. I think I am partly to blame for being careless in using it. The reason I dropped off the last two terms is simply to say that unless our question is about our likelihood of bumping into intelligent life, I'm not so interested in those last two terms. I just want to know whether life is out there. So it's not so much setting them to one as saying those last two terms are things that SETI can think about, but aren't terribly germane to our thinking about whether we belong in this universe. If we consider belonging in this universe to be we're sentient representatives capable of spirituality, capable of inter-individual communication of the highest degree, then we really need to only go as far as intelligence to address that question, and that's why I dropped off the last two terms. Okay. And sorry for all carelessness in my presentation of the rest of that equation.
Other questions for Stephen? Yes. In view of the enormous diversity of life that evolution has come up with, would it not be possible to say that all these amino acids that have been effectively ignored by biology give us a pretty clear indication that there are some very heavy constraints as to what can be built from them operating?
Excellent question. Very strangely to those who aren't involved in the field, astrobiology and this sort of cosmological inquiry is surprisingly closely linked to genetic engineering and an emerging field called synthetic biology, which is really just extreme genetic engineering. We now have, in the scientific community, we have the technologies to change the most fundamental aspects of living organisms. It's yesterday's news to take a gene from an ice fish and place it into a strawberry to stop that strawberry going mushy. Today's news is that we can design genetic codes that contain amino acids that have never been used by biology as far as we can tell. Now, that emerging frontier of synthetic biology is perhaps the best empirical proof we have that there are surprisingly few constraints on what is possible to incorporate into genetic coding. Now, what is possible to incorporate is a long way short of what is sensible to incorporate. And that's where I think the subtlety of this question is probably going to come down to saying we can almost think as if amino acids are Lego building blocks. What would make a good set of Lego building blocks if I simply tell you that I'm going to ask you to make a very wide range of structures and I'm not telling you ahead of time what they are? Could you make a good decision or a bad decision? Or really, is any set about as good as any other? In terms of pure constraint, surprisingly little seems to exist. In terms of subtle good choice versus bad choice, it's a wide open question and one that fascinates me.
But you can, in fact, there's a pretty strong limitation on what you can build with Lego blocks. And it's constrained by the way in which the studs are put and so on, which presumably is a similar thing to the way in which the valency links are making things possible.
Yeah. Now, forgive me, I think I heard most of what you said there. So you're saying that if we take on board the idea that a genetic code is constrained to put similar things next to one another, then that would put constraints on the alphabet? Is that was what you said?
Yeah. It's the way in which they fit together.
Oh, sorry.
The way in which they fit together.
Oh, the way in which they fit together, it's very cartoony, but the reason I drew a sort of green squidge at the bottom there was to say that this backbone is surprisingly boring and constant, and what you hang off of that backbone is surprisingly variable. I think there are actually very, very, very few constraints on what sort of side chains are possible for an amino acid in order that you can simply string one amino acid next to another one. And in fact, our host may be even better qualified from a biochemicals perspective to comment on that. But my take from synthetic biology is no. Barring steric hindrance, which is where you literally put a sidechain on that's so physically large, you can't put neighbors next to it. Barring that, you can do just about anything. And in fact, perhaps a secondary line of evidence that I could quote for that point of view is to say that actually biology doesn't just use 20 amino acids, it uses hundreds, if not thousands. It uses 20 within the genetic code. but things such as plants and fungi in particular have all sorts of extraordinary metabolism for modifying, changing, and incorporating different amino acids after that decoding stage is complete. And so the wealth of building blocks, really, if there are constraints, we've yet to understand them.
Thank you.
Other questions? Yes, over here. So,
I think you may mention that Darwinism destroyed the old view of the great chain of being from the lower and become the lower grade. You mean it's wrong, but for us sometimes Darwinism was interpreted that is just evolution from the lower parts to the higher parts gradually. Could you please explain that a little bit more?
Okay, let me do my best, if I've understood the question correctly. The Scala Naturae really implied to early evolutionary thinkers a staircase, that species were ascending, and that every step of evolution was necessarily taking a step upwards towards a higher state of being. Under Darwin, it's not that there has not in some lineages been an increase in complexity. He's quite happy to say yes. Some lineages have gone from being single-celled to being multi-celled, have gone from being multicellular to containing complex neural machinery. However, other lineages have been quite content to stay single-celled, and they're thriving 4 billion years later. So it wasn't so much that he is saying that there is no ladder worth thinking of. It's rather saying that when we look at the natural process by which evolutionary change occurs, we see no necessary change that creates increases in complexity, increases in sophistication. It's a possibility, but it's not an inevitable outcome. That would be an orthodox reading of Darwin, at least from the 20th century point of view. And it may be that as this debate goes further now, we may have to reevaluate that. But certainly, if you look at what Darwin was thinking and what people were thinking as they read him and worked for the next 50 to 100 years, they were simply saying, okay, we need to lose this intuition that there has to be a drive towards us, because that's obvious. Actually, cockroaches, bacteria, oak trees, earthworms, everything that's alive, by the very fact of being alive after 4 billion years, has shown that it has come up with a very good solution to the problem of fitting its environment. Does that help at all? Okay, thank you.
Can I just come back to the sort of a little bit the earlier discussion as well, Stephen? I was wondering if there are experimental data. I'm thinking of this thing you introduced briefly, the kind of triplet codon escape theory, where basically it was transfer RNAs that selected out, in a sense, with their binding constants to different amino acids, gave us clues about the origins of the genetic code. Are people actually, I mean, we've still got up on our screen what you have behind you, the wonderful picture of all these different amino acids, you know, which never got used, the poor neglected amino acids.
Yes.
Has anyone done any systematic experimental data, not just computer fitting, but experimental data looking at binding constants with all of those, you know, souped up with all the different transfer RNAs you can generate, to actually see what happens, you know, to see if there's any special about the ones down the bottom in terms of...
Now, a great question. As far as I'm aware, the answer is a simple no. It tends, as you well know, to be very slow and very expensive to do that sort of experiment, at least relative to computer modelling. I strongly suspect that far more of that has been done than we are currently aware of in the scientific community, for the simple reason that those most motivated to do exactly that study are those who are pushing forward synthetic biology. They are looking to make, for want of a better quote, unnatural protein products that may have commercial applications. And they are very eager to do that under copyright and under patent, so that the products that they're able to produce are marketable. So really, the irony for this sort of line of thinking is that part of it is about as cosmological and deeply scientific in the sort of philosophical sense as one could wish for. But a lot of the empirical data that we wish we had is probably coming from people whose interest is so commercial that we won't see their data until long after they've produced whatever it is they're producing. Craig Venter would be one of the key players here. He was the guy who back in the 1990s essentially tried to patent the human genome, and very thankfully was turned down in that effort. Well, he's sort of disappeared for about 15 years, but he's now back and is very interested in synthetic biology for creating protein products that have never seen the light of day within naturally evolving systems. And one read on that is because that would evade the reasons why he was not allowed to copyright human genome. If he can show that something has never existed naturally, he has a much better claim to own it commercially. And the sort of work that they may be doing, incorporating unnatural amino acids, whatever we're seeing in the scientific literature right now, maybe I'm paranoid, but I would suspect it's a small proportion of the work that's actually being done.
So if we do find life on other planets using the same amino acids, unusual ones that he's using, we could undermine his patents.
That would be a wonderful turnout.
I think we've got time just for one last question before coffee. So, Ernest Lucas.
Thank you. It's another sort of experimental question following on from what Dennis just said. I would divide amino acids, if you like, into two broad groups. Those that would be the background chains, and the other one is those that are important for the active sites, which need there to have interesting molecules, interesting sides to them. Lots of the ones you say are ignored seem to have carboxyl groups and OH groups, if I'm reading the picture right. What about thiol groups, pyrimidines, pyridines, and so on? Has anything been done experimentally to see how important the active site amino acids are as compared to simply the background chain ones?
Yeah, and now I'm sorry, I'm getting some weird audio effects there. I don't know if you were getting them too, but I think I heard everything I needed to hear from what you asked there. A wonderful question. The way that I'm thinking about the problem is really one of taking a question that was speculation only and asking how we can begin to bring it within scientific inquiry. And being a computer guy, what I'm interested in is modeling proteins that contain other amino acids and asking as far as we can what sorts of properties, what sorts of different or similar things do we get when we start using different amino acid alphabets. And as you probably well know, the state of modeling proteins right now, it's still an enormous challenge, The progress that's been made in the last few years is saying that we're beginning to get a handle on some loose predictions on the sort of structure that you're going to get out of a given chain of amino acids. Our ability to predict function on a computer is still pretty much zilch, unless we're talking about very minor modifications of what nature has already produced. So, in terms of the work that I'm doing right now, I'm thinking at a much simpler level than your very sophisticated question is asking. I'm interested in saying, do we get fundamentally different protein folds if we start incorporating 2 or 3 different amino acids? Purely because I think that's a question we can begin to answer. I dream that 10, maybe even 5 years from now, we may be able to start to do the function mapping, sequence of amino acids to function mapping, that would render your question far more tractable. I think until such time as that's possible for poor computer geeks like me, it's going to be down to experimentalists such as yourselves to tell me whether you can make any headway on that, but I would love to see that addressed any which way.
Okay, well, I think we've come to the end of our question time. We're about to head into coffee, tea. Stephen, I want to thank you again very much indeed for your great talk, so let's just do
Well, thank you for bearing with me. I've been pretty much half asleep for both of them, so I really appreciate your patience and good luck with tea. And I'll see you tomorrow morning.